Good afternoon, February 25, 2026, Fanshawe College, London, Ontario, CNTL3020, 26 Winter, Controls 2 course, week 7. Alright, cool. Let's start that presentation again here. Good. So, this is what we will be talking today about, today. We're going to review some logic gates, some truth tables that have to do with the logic gates, and we're going to look at some of the Boolean algebra laws and theorems. The reason why I'm giving you this is because, next week we're going to start some PLC programming labs, and we already have gone through the introductory to the ladder logic diagrams. Now, the ladder logic relies on the logic, the logic in our understanding when it comes to the truth tables and the Boolean algebra type of logic. So we need to know that. So to some of us it's going to be some refresher on these things here, logic gates and truth tables, and we really need to keep doing some exercises with the Boolean algebra, because when you're going to, if you find a job, if you end up working in this field, this type of logic is going to be your bread and butter in controls when you're going to design, especially when you're going to design and troubleshoot certain systems. Okay, all right, so let's start this one here. First logic gate, it's an inverter logic gate. This is the symbol of an inverter, and here is the truth table of an inverter. It only has one input and it only has one output, and whatever you see that inversion bubble in the symbol of that, at the end of the symbol here, that inversion bubble is the NOT bubble. So here is the input designated or tagged as A. Here is the output tagged as Q. And the truth table is if A is 0, Q is 1. If A is 1, the output is 0. So if this is true, if this is false, this is true. If this is true, this is false. It's an inverter. It inverts whatever it is on that. The Boolean expression for that is Q, which is the output, and sometimes you're going to have the letter Y in there. So, like in this chip right here, see, and the Q equals not A, all right, or Q equals, here is the A not. So that is the symbol. And sometimes when you're going to see certain literature, when somebody was writing and didn't have access to those special characters, they are going to put like a little apostrophe right beside that. So that also means, same as that little writing, a little bar, that bar means not. So over here you could just say, instead of the Q, where are we here? There. You could just say over here A, which is A, right? And over here you could say not A or A not. Or you could say A with apostrophe here. So that's the same thing. All right. The dash above A turns A into not A. In binary logic, there are two logic states. Binary, two logic states, 1 and 0, or should we say 0 and 1. The opposite of 1 is 0, and the opposite of 0 is 1. Therefore, not 0 equals 1, and not 1 equals 0, and here is the expression just like that. So this is something that's called a Boolean algebra, as opposed to the regular algebra. Okay. And if you want to see some of the TTL logic, the 74 series, so that's a TTL, you will probably end up doing certain exercises if you haven't already. The inverter chip is, well, forget the SN, there's some designations that mean certain things of certain type of a chip. 7404. TTL stands for transistor logic, so that means the circuitry inside that chip is made out of transistors. So we have the VCC, voltage supply, which says for V voltage, collector, which means all the collectors of the transistors are connected there. But VCC is the main power supply, and here's the ground. So in this 14-pin chip, the pin 14 is the supply, power supply voltage, and pin 7 is the ground, well, the ground, or the negative rail, if you want to call it that way as well. And in order for that to work this way, you have to make sure that the power is supplied. If you don't supply the power, this thing is not going to work. Just like the television set or computer. In order for it to work, you have to turn that on. All right, 7408. 7408 by the TTL logic. If you got CMOS, then there's well, you can have also a CMOS, but TTL is the most popular. And when you do the exercises, you're going to in the lab, you're going to use those. Okay, so the logic symbol of AND gate, as we already know, it has two inputs at least. Can you have multiple, more than two inputs AND gate? Yes, you can. But the most basic version of the AND gate is two input AND gate. And I see here, in this case, the output is tagged as Y, as opposed to, what are we having here? As opposed to over here, the output was tagged as Q. It doesn't matter what you label it, as long as you stick through with the same page. Well, it wasn't. See that? There's Y's, Y, right? So A and Y, Q, whatever. All right. Just so you know, it's not like Q. The Q always has to be tagged as an output of inverter. Sometimes people are going to label it as different ways. So the truth table of the AND, already we know that because we have done the lab, and I asked you to produce a truth table for the gates, and one was the AND gate, and I think an NAND gate as well. You have drawn that, and just as a review reminder, just to keep the retention, the output is going to be true, because now we are using new terminology right now. Since we started doing the ladder logic for the PLC programming this week, so we have introduced ourselves to the terminology such as 0 being equivalent to false. Okay. Or 1 being equivalent to true. So I'm going to use that terminology interchangeably. All right. So in AND gate, obviously both of those inputs have to be on, and in order to produce the output. So both of the inputs have to be true in order for the output to be true. And you can substitute, or you can draw an equivalent logic circuit to each rung, or to the whole collection of rungs in the ladder logic for the PLCs. And sometimes when you are going to be faced with a problem that you need to come up with the Boolean expression, simplified Boolean expression, because when you design a system, you're going to draw this that needs to perform certain logic state. The other piece of equipment has to perform something else, and you can connect those in a very complex way. But sometimes when you look at the whole big picture, and if you come up with the Boolean expression for that, you can simplify that, and you can use less pieces of equipment in order to make the whole production line or the whole system, whatever it is, work the same, do whatever you need to do with less complexity. And that's the whole idea. This is why I'm showing you this stuff here. Now, you're not going to have a complete understanding right away, because this is one of those things that you need to kind of drill some exercises in order for that thing this thing to enter your bloodstream, if I can say that. All right, so here's the symbol for logic AND gate. Boolean expression is the output equals A, and see that in normal algebra, the regular algebra, this would be the symbol of times, A times B. But in Boolean algebra, we read this thing as AND, that dot. And in a way, it works quite similarly to if you had the regular algebra. So the calculations would be similar. The result would be similar if you're multiplying. But we read this as AND. So the Y output equals A and B. And if there were more inputs here, they would go and C and D and E or whatever. Okay? Whatever the number of inputs. What's that? There. Sorry about that. Okay. And 7408 is the chip if you want to play with that. And of course, it's again, it's a 14-pin chip, and this is not a surface mount. This is the DIN, dual inline chip package. So pin 14 is the power supply, and this one here, the 74, the TTL logic, this one here is the 5-volt logic. You can also have 3.3 volt logic for some smaller chips. So in this case it's a 5 volt. We're not going to get into the what makes it 1 and what makes it 0. If you want, you can just research on your own the TTL logic levels or CMOS logic levels. They're going to be slightly different. What is it that the input is going to interpret as 1? There's going to be certain level of the voltage, and then there's going to be no man's land, and then what is it going to be interpreted as 0? There's going to be a range of voltages from 0 to certain voltage, 2 point something or something like that, and then 3 to 5. Or I would just have to go and you can Google that if you want. It's going to be considered as 1, so that's going to be the inputs, and on the outputs, also the table is going to show you what it is going to actually guarantee you to give you on the output between what and what is going to be considered as 1, and what voltage is going to be considered as 0. So I'm just giving this thing to you as a side note. So I'm pretty sure it is going to be given to you in other subjects that have to do with this type of electronics. But we have to go through this logic again. We have to go through this logic because we are going to do some logical or logic circuits when programming the ladder logic for the PLC modules, and so that we have to have this concept fresh in our minds when it comes to this. Then there's an AND gate, which is not AND gate. See that inversion bubble right here? The inversion bubble means that it is turning whatever it is on the output, it's turning the opposite way. And since we're dealing with the binary system, it's going to turn 0 into 1 and 1 into 0. Simple. So the truth table is just the opposite of an AND gate. So if you have false on both inputs, you're going to have a true on the output. Unless you have true on both inputs, you're going to have a false on the false statement on the output. So this means in this case here, we're going to have 5 volts as 1 and 0 volts as 0. Well, the 5 volts is a range between 5 and a little bit less than 5, and the 0 range is between 0 and a little bit higher than 0, so the tolerances are met. So by saying that, this is the 7400, for example, the TTL logic, again, 14-pin chip. In this case, pin 14 is the power supply voltage, pin 7 is the ground, and it has to be on. The power has to be supplied in order for this to work as such as the gate. So this one has quadruple gates. It's a 4 gates. It has on those NAND gates. Now, remember when we were talking about the PLC module, the ladder logic programming, that is going to be, the software is going to be, well, it is interfaced with the physical PLC module, and we're going to have inputs on one side, left side, and we're going to have outputs on the other side, on the right side. So with the PLC module, that output is going to be 24 volts, energizing whatever needs to be energized. Other logic gates, we have OR gate, truth table, either one in OR gate, either one or both. If there is 1, there's going to be 1 on the output, and the Boolean expression is A or, see that plus sign? We read that in Boolean algebra, we read that as OR. So A or B. That's the expression on the output. Now we have NOR, which is the opposite of OR. And you see here we have that bar on top of the final expression, the most simplified expression here. The output is because we have that inversion bubble here. That means that the output is going to, the whole output is going to be inverted. And that is the symbol that signifies the inversion of that. So you see these two truth tables here are just the opposite of each other. Wherever is 0, there's 1. Wherever is 1, there's zeros. Yeah. A or B. Now, we have exclusive OR exclusive NOR. Let's take a look at exclusive OR. The difference between OR and exclusive OR is that in OR gate, we have as long as one of the inputs is high, then the output is going to be high. And in this case here, if both of them are high, the output also is going to be high. In exclusive OR, as opposed to just regular OR gate, see there's that little extra tilde, not tilde, but well, curved bar here. And that is the symbol of exclusive OR gate. As long as one of the inputs is on, then the output is going to be on. However, if both of them are on, then you're going to have no output. That's the only difference between the OR and exclusive OR. Exclusively, it's either that or that, but not both in exclusive OR. And here is the Boolean algebra symbol. There's that little or plus sign enclosed in a circle. So that's the Boolean expression. And of course, exclusive NOR is the opposite of exclusive OR. So you see that this table is just a negative version of the exclusive OR is negative version. Well, these are negative versions of each other. Should go forward, not backwards. All right. So Boolean algebra laws. Let's go through some of those. Where are we here? Here's the Boolean expression, and this would be, well, something closer to that ladder logic that we're going to be dealing with. But this is the most simplified version just to express the logic. So, when we have two inputs on the gate and we have one, whatever it is, and the other one is going to be, the other input is going to be stuck high permanently, we're going to get high on the output. No matter what this is going to be, because that's the AND logic truth table. If you look at the AND logic truth table, that makes sense. So in parallel, we can just see that thing visually. This is the input A. This is the, well, the other input, but it is stuck on high. So this is true. This is false. It is going to give us true. How do we know? Because we're going to have that imaginary current being able to flow through here, always. No matter what you do with this one, the current is going to go, the current will be able to travel from one end to the other. And this A and 1 equals 1. This Boolean algebra law or rule is called annulment. Because we're annulling the other input. We don't care about the other input. So we could just say it's don't carement. I think I just invented a new word. Alright, so now here's another one. Identity. And this is the OR symbol. A or 0 is always going to give us A. And here is the visual expression of that. Whatever the A inputs, this is the input that would change. And this one here is always false. So the output is going to follow whatever you do with this one. And this one is going to be, yeah, whatever. All right? It's like we don't care. So the output is going to be whatever you do with this. And it makes sense. You close the switch, you get the current flowing. So if this is true, remember, what is the software, the PLC software asking itself when it sees normally open contact? It's asking itself a question, examine if closed, because it's open. So see if it's closed, see if it's closed, see if it's closed, except it's asking itself that, 1,000 times per second. So examine if closed, I'm just applying the ladder logic here as well. So that's the identity. When you see that expression, A or 0, always going to give you A. Now, another identity. A and 1 is always going to give you A. So the output is identical to the, so A or 0 is going to give you A. A and 1 is going to give you always A. It makes sense. The output is going to follow what's going to happen in that contact. So that this is identity and this is also identity. Another annulment, because we always have, so annulment, that means we're going to not care about something. We're going to make something invalid or not important. A and 0, if you look at the truth table, that is always going to, whatever we're going to have on A, as long as the other one is stuck on 0, we are going always to have low on the output. So we're annulling that input here because that is stuck. And this is the AND. See that dot? And somebody didn't have access to certain characters to put the dot in the middle, and you're going to see sometimes that too. So here's the visual expression. See that? We're annulling this. Got it? All right. Idempotent. Hope I'm saying it right. A or A is going to give us A. Right here. Doesn't matter which A we press. Whatever is input we're going to press, it's always going to give us an output that is going to be true. As long as one of them is true, this rung is going to have a condition of true instead of condition of false. How do we know? Is that if we see the imaginary current being able to flow all the way through. So either through here or through here, as long as you close one of them. Here is an OR gate kind of a thing. So if you have A or A in some kind of a long Boolean expression, you can simplify that to just A. Or if you have B or B, that's going to be B, of course, right? You know that. Another idempotent. If you have A and A, you're always going to have A. You know, if you have both of them, that's the end, both of them are going to be on, then you're going to have the rung as true. Right? So that's these here. Now, more rules. Alright, it's a double negative. If we have not A, we're going to have A. A? So that is double negative. Complement property. A or not A is always going to give you 1. When you have A or whatever is stacked high or low, doesn't matter, the output is going to follow what? So it's OR. If this one here goes either way, well, but in this case is not A. So look what's going to happen. This is A and this is not A. If you draw a dotted line here, you could just have that. You move that means that is going to open that one, and you close that one, that's going to open that one. You're always going to have A or not A is going to always to simplify into 1. Another complement. A and not A, because it's an AND gate, both of them have to be on. And not, sorry, A and not A, A and not A will give you always low on the output. See here? If you close this, that one's going to open. If you close that, that's going to open. You will never make that rung true. So it's a complement type of a property. Then, of course, here's the commutative property. A or B equals B or A. Just a formality. And of course, in the AND type of logic, A and B equals B and A. Right. Where are we here? And here is the good old De Morgan's theorem. Here's the expression. You might have to use that when you're going to solve some kind of a complex equations in order to simplify that. When you see this, when you see A or B and the whole thing is inverted, the whole output, the whole OR operation is inverted, it's the same as separately inverted A, and then there's AND symbol. So invert and replace OR with AND. See that here? That here, you're going to have the separate inversion on that, and you're going to substitute the OR with the AND symbol. Same, it works same the other way. If you have A and B and the whole output is inverted, it is same as separately inverted A or separately inverted B. That's the De Morgan's theorem here. Shall we prove that the De Morgan's theorem works by looking at the truth tables? Let's do that. Here is A and B, so A and B equals inverted A or inverted B. Here's A and B, so that's on here. We have the output of the A and B. We invert that and we're going to have inverted A and B, A and B. So looking at the truth table, if those both are zeros, so if you perform the AND operation, you're going to have 0, 0, 0, 1. That's the AND operation. And that's the inverted A and B is going to give us the opposite of the AND. So here's the inversion. Not A and not B inverted separately. 0, 0. Here's OR. Alright? So if we separately invert A and separately invert B, we're going to have 1 here and 1 here. Perform the AND operation on that, you're going to have 1. See? Inverted separately A and B, so you're going to have 1 here and 0 here. Forget that those, right? So, and you perform the AND operation, and so 1 and 0 is going to give us 1, because if you look at the truth table, and so on. So that's the proof of the De Morgan's theorem, and that's the you can say, you know, later on you can analyze this thing for yourselves by looking at that. I just showed you how to do a couple of those lines. All right, that's the end of that one. Now let's take a look quickly at something here. Yeah, maybe I should keep that. Yeah, I still have it. Right. Got it? Got it. Okay. How are we doing with time? Oh, we're still okay. Could just do a couple of worksheet, some exercises here. Boolean Algebra and Logic Gates worksheet, so questions based on that. Create a truth table for the expressions of Q equals not A and B. Wow, alright. Q equals not A and B, so A and B is here, and what is this? OR B. Okay, so we're applying the OR operator, so we have the A and B here, and just for ourselves we're going to look at the over here we're going to look at just these here. Alright, because here's the A, here's the not A, or A not. You see there's apostrophe here instead of the bar on top. So we're going to be interested in the inverted A, so this is what we're interested in, and we're going to use the OR operator. So that is going to be the truth table. See here, 1 or 0 is going to give us 1. So that was the create the truth table for the expression of Q, or with output equals not A and B. Now, of course, not A. That A it's an explanation here with A with apostrophe. Sometimes you're going to see that. Simplify the Boolean expression using the Boolean laws. And here's the y equals A and 1 and A and 0. Alright, now when we look at some of those here, where do we see here the properties? A and 1, what is that going to give us? It's going to give us 1, is it? No, it's going to give us A, right? A and 1, where do we have that? Is it AND? Yeah, it's AND. There you go, identity. A and 1 is going to give us A, whatever is A. So, whoa, what did I just do? There you go. Got it back. So here you see that A and 1, that turns into A. Alright. Now, A and 0, that is always going to give us 0. And if you look at this here, A or 0, the final answer to that is A. Y equals A. You see here? Now, when simplify that, when you have this one here, you have a bunch of different pieces of equipment, different sensors, and sometimes maybe you don't have to use so many sensors in the system, on the production line. Simplify it. If you simplify it, it uses less energy, and if you simplify it, if you have less pieces of equipment, then there's less things to break, and it's easier to troubleshoot. So that thing here, y equals A. That's it. When you have this expression, I'm going to give you this to work with as practice problems. Now, one thing also I'm going to include in this here. How are we doing with time? Doing great. What are the orders of operation if you have longer expression and you have no brackets? And what does it say here? When working with Boolean algebra, the following the correct order of operations, also known as operator precedence or precedence, it is crucial because, just like the standard arithmetic, changing the order can completely change the end result. If Boolean expression does not contain brackets, you should follow this hierarchy. And see here, not. And this is the symbol that expresses not, or a not, the bar on top, or sometimes you're going to see the letter with the apostrophe. So the same thing, not. The not operator or negation has the highest priority. It always applies first to the variable or sub-expression immediately following. Right? So first we use the nots. Then number 2, and, or. So and operation, conjunction, so and, sorry, and not that or, and. So you will see that symbol, sorry, and, yeah, that symbol, or you will see that whatever this thing is called on the keyboard. Because sometimes people just write this thing in text. So if you see that, that also means, is the lecture posted on FOL? I will finish notes. Yes, I will post that after we're finished. So later on tonight I'll post that. I just have to convert it to PDF version. Yes. Cool. Yeah, I was just reading the chat lines here. So then we do the and first, same as the multiplication in the regular algebra. And then we do the ors, or the pluses. Here's a summary of the table. Example. When you see here, what do we see here? We have this expression. What do we see? What do we do first? The negations. So that is going to be done first. Then this AND operation is going to be done second. And then this OR operator is going to be applied. Oh, wait a second. Here it's explained here. Not first. Then AND, not B and C. And finally, you're going to OR it with A. What is that on type procedures? If you have multiple operators of the same level, you just do it from left to right. And A and B and C, A or B or C. So the operators are on the same level, same weight. Okay, so you have something to work through as a practice problems, and I would strongly recommend that you do that. When I say that it's a good idea for you to do this, I'm also going to, maybe in a week or so, I'm going to give you another quiz for that, and it's going to be a practice quiz online, and then again test. So by the end of this first test, we know that it is important to go through the exercises, because, well, the unit test, plus the final exam is on paper and in person. So you should have that knowledge and the only way to do that is by doing the exercises. Cool. In the labs, I noticed I'm just doing those final. I gotta give you the midterm marks by the end of Friday. So please make sure that if you have any kind of outstanding work, upload it. Right? And of course, there was a couple of cases that I had that I say I need one PDF file with all the pages on it, one integrated PDF file, otherwise it's unmarkable. So it's not that I'm giving you 0 on that, it's because you know what's supposed to be done, then you are giving yourself a 0. I'm just a mark printer in this case. All right, so don't shoot the messenger, or don't shoot the printer. All right, cool. Thank you so much for your attention today, and I will see you when I see you next week, or some of you are going to see my pretty face tomorrow during the labs. Thank you, and till the next time.